In the last lecture, we had just started with the partition function, and I had introduced you to the partition function Q, which was summation of e to the power minus beta Ej. The Ej telling you about all the energy states that are possible, that are available for the particle. And beta was nothing but I had told you that it's supposed to be 1 by kt. We'll not derive that, but you have to accept it for the moment. The partition function, of course, if it was large, then everything was in the lower lying energy states, and if it was small, then everything was spread over all the energy states. One could estimate all physical properties if one had the knowledge of the partition function. For example, we had seen with the ensemble energy, the average energy, it's only the average which we can measure. We had also seen how to get the average pressure. We had also seen average pressure over here. We had seen how to get the heat capacity, CV, for monoatomic gas, which had only 3 degrees of freedom for the energy. We had for the diatomic gas, which had the 3 translational degrees of freedom and the 2 rotational degrees of freedom, and then the vibrational states, the ground state energy for the vibrations, and at the excited states being populated at higher temperature, and of course the pressure. And from here we had also derived the ideal gas equation of state, PV is equal to nRT. Okay, now we'll move on from here. Okay, so in the last lecture we had seen some of these partition functions, and we had told you about the molecular partition functions and then used them in order to derive some of these properties for monoatomic and diatomic gases. So now, how do you get from the total partition function Q to a molecular partition function? Now think of the total energy E, which I have subscripted over here with L, as being the energy of all individual particles. So we have N, capital N particles, or capital N molecules, whatever, and epsilon A happens to be the energy for molecule A. Epsilon B happens to be the energy state for molecule B. The subscripts I or J or K, whatever, they denote a particular energy state for the molecule. So the molecule has loads and loads of energy states. I denotes that it is in the ith energy state. J denotes that it is in the j. These could be the same, these could be different, of course. If I'm talking of independent distinguishable molecules, right? So I'm distinguishing them by the subscripts A, B, C. And they are independent. And since they are independent, their energies don't talk to each other. I can just add up their energies. Okay. So if the energies can be added, then the partition function Q, which is nothing but sigma e to the power minus beta EL, can be written as this sum of all the energies, right? Where EL I can expand as epsilon IA plus epsilon JB plus so on and so forth. And since all these energy states, I, J, K, these are indices which run over the energy states of a given molecule. And one molecule doesn't talk to the next one. So I can independently sum them up, right? I would have all the energy states of molecule A. I would have all the energy states of molecule B. Likewise for C, D till molecule, all the capital N terms. If you look at this, this has a structure similar to the structure of capital Q, right? Instead of using EL, what I'm using is epsilon I. So this is nothing but it's another partition function. Instead of being for the complete system, it is for one molecule. And I represent that by small q. I put A to represent that this is for molecule A. Then this is nothing but a product of small q's. Right? How many times? Capital N times. And since all these QA, QB, they are identical molecules, so all the energy levels happen to be identical, so all the sums happen to be identical, I would have capital Q is equal to small q raised to the power n. And now mind that small q is just a function of volume and temperature. Alright. Now it so turns out that always your molecules cannot be distinguished. They can be distinguished, for example, in a perfect crystal. I can take the crystal coordinates or something. I can just label them 1, 2, 3, 4, so on and so forth. But more often than not, for example, in gases, the molecules happen to be indistinguishable. And when they are indistinguishable, I can no longer label these. You see, I've removed those A, B, C over here. So I can no longer label them. Yeah. Still, they are independent, so I can add up the energies. That is not a problem. But I can't label them. Again, capital Q is given as a sum, but then I cannot, since they are, I do not know whether it belongs to A, B, or C. I cannot separate the sums I, J, K over here. Okay. Anyway, I'll not go into much details over here. But if I cannot distinguish these molecules and I keep on doing that summation over and over again as I had done over here, had I done this kind of a summation, I would have overcounted my states. And to avoid overcounting, the prescription that is given is to divide by n factorial. Okay? So one can debate about this and learn this in more details, but for this course it's enough to know that when you have indistinguishable independent molecules, then what you need to do is q to the power n divided by n factorial. That is what you need to use. Okay. All right. Yeah, there's a lot of discussion in McQuery, and well, not lot actually. It's very little rather, where it treats different kinds of particles and shows that how division by n factorial is possible. But let's just take it for granted for this particular course. Yeah, it's very simple. When you have indistinguishable molecules, you need to divide by n factorial. All right. Now, if you look at the decomposition of the molecular partition functions, so we need to decompose the molecular partition functions, and if you see how it looks like, then the total average energy of the whole system comes out nothing but n times the average molecular energy. Okay, you can do this d log q by dt. Well, this was the formula for the average energy, right? Minus d log q by d beta, or kt square d log q by dt, holding n and v constant. What you get is n kt square d log q by dt. Even if you're using for the indistinguishable molecules, the n factorial happens to be a constant as far as t is concerned, right? So you would get that, and this term over here, well, actually even before that, this term over here is nothing but the probability of the particle being found in the ith energy level. Now this is the probability of a single particle, and you multiply the probability with the energy, so that essentially, and then sum it up, that essentially gives you the average energy of the molecule, this term, right? Um, so yeah, what saying exactly the same thing over here. The probability that the molecule is in the jth molecular energy state by J is equal to e to the power minus Ej by Kt by Q. Alright. This is exactly analogous to the probability that we had defined earlier when we were talking in terms of the energy of the complete system. Now we are talking for energy of one particular molecule. Further, you can break down the energy of a molecule into translational, rotational, vibrational, and electronic energies. Okay, and if you break that down, if I can add it up, and we know that we can add it up because the translational, rotational, under the harmonic oscillator, rigid rotor approximations, we're talking about those things only. We know that these energies are not dependent on each other. The vibrational energy doesn't depend on the rotation or the transition or the electronics, or any of them doesn't depend. And since we can add them up, Q then of course gets multiplied. We've seen this earlier, so it's the same thing. Q, which would be a function of volume and temperature, would be Q translational, Q rotational, Q vibrational multiplied by Q electronic. Now, we'll of course deal with this very soon, but food for thought. Q happens to be a function of volume and temperature. Which of these terms depends on volume and which of these terms depends on temperature? Okay, we'll discuss that later. Okay, so if this is the thing, then the probability that the molecule happens to be in IJKL state, where I is the translational state, J happens to be the rotational, K is the vibrational, and L the electronic state. So what is the probability of being in that particular state? The probabilities are simply multiplied with each other. So that would be e to the power minus epsilon I translational by Kt divided by Q translational multiplied by e to the power, which is the probability of being in the translational energy state, e to the power minus Ej rotational by Kt by Q rotational, which would be the probability of being in the rotational state. Likewise, the probability of being in the kth vibrational state, and multiplied by the probability of being in the Lth electronic state. Okay. And if you want for only one particular energy state, for example, you want the kth vibrational state, then all the rest of the probabilities, they have to be in one of the translational states. So the translational probability has to go to 1, right? Which means I just sum up over all the possible translational probabilities, which is sigma I e to the power minus epsilon I translational by Kt, which is nothing but Q translational, right? And divide that by Q translation, so that goes to 1. In fact, the first 3 terms, the numerator, divided by the first 3 terms, not the 3, 1, 2, and 4th term of the denominator, that all go to 1. What remains is just e to the power minus epsilon K vibrational by Kt divided by Q vibrational, and that is the probability of being in the vibrational state. So you could have pi k vibrational I could write this fellow pi ijkl as pi I translational multiplied by pi j rotational multiplied by pi k vibrational multiplied by pi L electronic, right? And if I were looking for the average energies, as I have done it in the past, I would again, this is just analogous to the energy of the entire system or the energy of the molecule, or I could even write now for each and every different contribution. The average vibrational energy, for example, happens to be minus dq vibrational by d beta, and this is also true for the translational energy, which would be dq translational by d beta, or for the electronic energy, or for the rotational energy, and so on and so forth, right? This is all analogous. So you can break down the energy into smaller and smaller units, uh, different contributions, and you can have your partition function likewise. Okay. Another concept over here is that of degeneracy. Okay. Now, come to think of states. When we say states, then we are counting each and every energy state. Okay. So, for example, if I have a square particle in a box. So I have a square box, and I have both the sides equal. Then, as you know, you get degeneracy you don't have any degeneracy when you have 1 1, but you have degeneracy when you have 1 2 and 2 1. Then I would say the first state is 1 1, the second state could be 1 2, the third state could be 2 1, the fourth state is 2 2. But when I say levels, then it means you distinguish levels by energy. So you have the first level, which is 1 1. The second level happens to be twofold degenerate, which is either 1 2 or 2 1. Okay. So now, instead of counting over all these states, I could count over all these levels. And when I count over all these levels, then I have to multiply by the degeneracy over there. Yeah. So it's exactly the same thing, except that you bringing in the concept of frequency, as you would do when you are dealing with averages of marks in the class or something. So this is what you do, right? Instead of counting over states, you count over levels, and this is exactly the same formula, except whenever we had the same epsilon j value, we've clubbed them all together and taken it only once and multiplied that by gj. That's all. For example, rotation, when you have a jth quantum number, it's 2j plus 1 fold degenerate. So you have the degeneracy 2j plus 1, and j goes from 0 to infinity. J goes from 0 to infinity, e to the power minus h cross squared jj. So that's the energy. Ej was nothing but h cross squared j into j plus 1 by 2i. So that's the energy of the rotational state divided by kt. Okay. So that's how we can introduce the concept of degeneracy. And this could be useful when you go to cases where you don't want to write things again and again. So, all right. Now, let us take a look at one of these specific examples. And in the previous lecture, when I had asked you to calculate the heat capacity of the monoatomic ideal gas, I had given you the partition function. Let's go and see what that partition function was. Okay, this partition function which I had given you was qv beta, or beta or t is same, doesn't matter, 2 pi m by h square beta to the power 3 by 2 times volume, right? Okay, so coming back here, let's take a look if we can derive this molecular partition function for a monoatomic ideal gas. Because if we can derive, then we would go and try to see how one could in general derive for any given system. And because if you can derive it, then from first principles you can essentially get all the physical properties of a system, right? and that is a lot of predictive power over here that we are talking about. Okay, so when I talk of a monoatomic ideal gas, it doesn't have any rotation, it doesn't have any vibration, so the entire energy happens to be translation plus the electronic energy, right? And I've already given out a bit of the answer over here, which I asked you a few minutes back. Q, which is a function of volume and temperature, is Q translational, which is a function of volume, temperature, and Q electronic, which is a function only of temperature. One can think about this. Now, let us take a look at the translational part of this. Okay. We'll worry about the electronic part later. So, let's take a look at the translational partition function. Now, I know that this molecule happens to be in a box whose edge length happens to be A, and let's just take A by A by A. So let's take a cubic box. And the partition function of this particular molecule, the translational partition function, is given by e to the power minus beta epsilon nx ny nz, and I have to sum over all these nx ny nz values. I know that epsilon nx ny nz is obtained from my particle in a box model, right? So I just need to sum from sum nx is equal to 1 to infinity, ny is equal to 1 to infinity, likewise nz, e to the power minus. So particle in a box gives me energies h squared by 8 ma squared, nx squared plus ny squared plus nz squared. So minus beta into epsilon. That's what this entire term in the bracket is, right? Minus beta into epsilon. Now I break up this epsilon, so I separate the x, y, and z terms, and then I can very easily, since neither of them is dependent on the other, I can write separate terms over here: minus beta h square and x square by 8 ma square, ny square, and for nz. Okay. And all of these values of nx, ny, nz, okay, they go from 1 to infinity. So let me just sum it up and show you that if I sum it up like this, then what I get is e to the power minus 1 into beta h square by plus e to the power minus 2 square for beta h square by 8 m square plus e to the power minus 3 square, that is 9 beta h. Okay, and all of these, both 1, first, second, third, all these summations essentially give you the same thing, right? Nx, ny, or nz just vary from 1 to infinity. So this is nothing but sigma n is equal to 1 to infinity e to the power minus beta h square n square by 8 ma square, everything 3 times. Oh, here. So Q translational, then I can write as this whole Q, right? Because of the fact that nx, ny, nz all go from 1 to infinity, and they are exactly identical, all these 3 terms. And remember, these box is a very large box, so your energies are, A is very large, right? So this A square is very, very large, and so the difference in energies is very, very small. So they're more or less like a continuum of energies. I can approximate that to be an integral, first thing. Okay, so instead of writing a summation, I approximate that to be an integral, and it won't make a difference if I start from n is equal to 0. Okay, if I start this integral from n is equal to 0, see, even n is equal to 1 is a very small value. Okay, so n is equal to 0 will not matter. So I can integrate from 0 to infinity e to the power minus beta h square n square by 8 ma square dn, and take the cube of that. Now this brings me to a standard integral e to the power minus alpha x squared dx is equal to pi by 4 alpha to the power half, which gives me 2 pi m kbt by h square to the power 3 by 2 times volume. Well, a cube, I would put that equal to volume. But 2 pi m kbt is equal to 2 pi m by beta h square to the power 3 by 2. And if I look at the previous one, 2 pi m h square beta to the power 3 by 2. So we have derived exactly the translational partition function for a monoatomic ideal gas, and this is what the partition function happens to be for the monoatomic ideal gas. See, it is dependent both on V and also on beta, right? Yeah, where was I? So yeah, so this happens to be only the translational partition function, and what you had done earlier, that the energy you had calculated in the last lecture, well, that's pressure. The energy, average energy, was 3 by 2 RT for a mole, and for one molecule it would come out to be 3 by 2 kT. You would do exactly the same thing, minus d log q by d beta. You would get 3 by 2 kV. I mean, it's always easy to work with beta, although I've written the expression as kt squared d log q by dt. It's easy to work by using minus d log q by d beta, and then at the end you would have gotten 3 by 2 beta, and then you convert it to 3 by 2 kBT. 3 by 2 beta in the denominator you would have gotten, right? Now the thing is that if you look at this partition function, that's completely translational, and what we had was that we had a Q translational and a Q electronic, and I have not used the electronic part at all. Okay, let's see what the electronic part would look like. So first thing is zero of energy. Where is the zero of energy? That's completely up to us to decide what is the reference of energy. So let me take for all different molecules, whichever I'm dealing with. Let's say that the ground state energy happens to be 0. Okay. So if I were to write my electronic partition function, which is just a function of temperature, because I don't change the volume, I don't change the molecule at all, right? It just stays at one place. It's not moving around whenever I'm worried about the electronic energies. Okay, so the partition function is nothing but summation of G, which is degeneracy, times e to the power minus beta epsilon. So for the ground state, epsilon happens to be 0. Okay, and for okay, so let me write this as EGS is equal to, since I've used the same thing, for epsilon E1, okay, so that happens to be 0, so it's only GE1, and usually, I mean, more often than not, your ground state is non-degenerate. There are cases where it is degenerate, but mostly it's non-degenerate, so this would also go to 1. GE2, whatever the degeneracy of the second state is, e to the power minus beta E epsilon E2. Now, if you look at the electronic energy levels, then you've already seen we did some examples of 1,3-butadiene. You've also done a lot of spectroscopy experiments with the dyes. You've seen that these are typically on the order of few tens of thousands of centimeter inverse. Okay. And given the fact that 1.986 into 10 to the power minus 23 joules is 1 centimeter inverse, Kb comes out to be 0.6950 centimeter inverse Kelvin inverse. Put these values over here for beta epsilon electronic is typically 10,000. Okay, wait a moment, please. Should have been here. 10,000 centimeter inverse by 0.6950 centimeter inverse Kelvin inverse into 1 by T, roughly 10 to the power 4 Kelvin by whatever temperature is. And even if I put a temperature of 1000 Kelvin, this comes out to be about 10. Okay, well, room temperature is not 1000, I'm still using a higher temperature. And e to the power minus beta, so minus beta epsilon e to the power minus 10 comes out to be about 10 to the power minus 5, which means for every one molecule, 1 lakh molecules in the ground state, there's only one molecule in the excited state. So we can as well ignore any of the excited states. So Q electronic is simply this fellow, and more often than not it's just one. So one doesn't really have to worry about including the electronic partition function over here. It's just Q translational which works out well. In certain cases, we'll not deal with those cases, but in certain cases where you have smaller values than tens of thousands, and when you come to atoms such as the halogens, for example, where you have a few hundreds of centimeter inverse energy gaps, then it makes sense to include at least the first excited state over here. Otherwise, you have enough number of translational states, okay, and more than enough actually, that all of these translational states can be filled up before one goes to a higher energy level in the electronic state. Okay, there are more translational states available than what you have. The more translational states compared to the number of molecules that are available. Okay, so for all these molecules you can very easily fill up all the translational states. So one doesn't have to worry about that. Okay, we'll meet in the next lecture where we will look at the partition functions for a diatomic ideal gas. Okay, we've seen for a monoatomic ideal gas how we derived it. Now we'll look at a diatomic ideal gas.